Okay, today we'll talk about queuing models. What are the parameters in queuing models? Or if you are asked to describe or elaborate or write some sentences about a queuing model, what are the points on which you need to focus on? Okay, we'll talk about that. Now, elements or parameters of a queuing system. What that is first element would, as all of us know, uh, suppose if I'm talking about a queue, there is an arrival. People arrive, they stand in the queue, get the service done, and leave the queue. Okay, usually that is what is supposed to happen. Okay, so input or the arrival pattern would be the first parameter. Now, what we'll assume is usually we observe that customers arrive randomly, but for the queuing model to be discussed in a proper way or in a proper mathematical way, we assume that the arrivals are Poisson in nature. Why? Because we'll be considering on an average how many arrivals are there per unit time. Okay, per unit time, lambda we will consider number of arrivals per unit time. It can be per hour, per half an hour, per day, or per 8 hours, like that. Okay, so accordingly, lambda would be decided. Now, since it is Poisson in nature, we observe that the probability of n arrivals would be lambda power n into e power minus lambda by n factorial. Those who are all aware of Poisson distribution would be knowing how this formula has arisen from binomial distribution, or this is the formula for Poisson distribution. Okay. The next parameter for a queuing model would be inter-arrival time. Means what? Usually it is not like that. The queue is fixed. There are certain number of people, they get served and then they just leave the queue. It is not like that. There'll be in between so many people who will be joining the queue, leaving the queue, etc. and all that. So that also has to be taken into care of. So there's something called inter-arrival time. Means what? Between the arrival of one person and the other person, what's the time taken? Okay, that would be called the inter-arrival time. Time between two successive arrivals. Successive means what? The one comes, joins the queue and get the service done and leaves kind. Successive means one after the other, by the way. Okay, so if the number of arrivals follow Poisson distribution, then inter-arrivals follow negative exponential distribution is the assumption. Exponential distribution, all of you are aware, guys. Again, those who are aware of continuous distribution, so exponential distribution, you will be aware. In case you have a doubt about it, you can just refer to my videos on my channel. Okay, so a negative exponential distribution. Now we'll assume that f of x is the probability that inter-arrival time is t units. Okay, means what? There after each 5 minutes there's a person joining the queue. That's the assumption. Let us suppose. Actually it doesn't happen. Usually in certain period of time, in 1 hour, how many people joined, how many people were prior there, how many joined after this, I mean after at 10 o'clock or something like that, after 10 to 11, in between 10 to 11, how many joined. If you observe, on an average you will take, you cannot say that queue is anyways always in a random fashion. People mindset is in a random fashion. So you cannot just say that people after every 5 minutes a person comes and join the queue. If I tell that the average is 5 minutes or 8 minutes, on an average per certain unit time, we will calculate what's the average time each person, I mean new person, is joining the queue kind. Okay, I hope I'm not confusing you. Okay, so f of x is the probability that the inter-arrival time is t units, 5 units or 5 minutes or whatever. So it is following negative exponential distribution. Now, usually we consider negative exponential distribution because exponential function incessantly increases. So until unless the power of has a negative sign, the function that we are considering doesn't converge. It goes into infinity. And then you can observe the same thing when you are finding solutions to differential equations, guys. All the solutions to differential equations are exponential functions only, if you observe. And then usually they tend to have a negative sign so that the solutions converge and not diverge to an infinite value. Okay, so f of x is equal to lambda e power minus lambda t is the inter-arrival time function. Okay. Now, inter-arrival time between 0 and infinity. Suppose if I am considering t ranges from 0 to infinity. Suppose if I split the interval from 0 to t and t to infinity, there are, let us assume that there are no arrivals in the time 0 to t. And then there is one arrival in time t to infinity. Okay. Okay, now see, how do I calculate the probability that there is one arrival after time t? Probability that there is one arrival after time t is nothing but probability that there is no arrival in time 0 to t. Okay. Yeah, there is no arrival in time 0 to t. So what I will take 0 to t lambda e power minus lambda t dt integrated from the limit 0 to t. Hence I get e power minus lambda t. You can observe this. This is a simple integration. Now probability that there is no arrival in time delta t is given by e power minus lambda. Instead of t, I'll write a delta t. Probability that there is no arrival in time t was given by, you can see here, in time t, no arrival in time t was given by e power minus lambda t. No arrival in time delta t is given by e power minus, instead of t, you have lambda t. Okay. Yeah. No, no. Instead of t, you have e power minus lambda into delta t. Okay. Now, if you expand e power minus lambda delta t in terms of e power x, this is what you have. Okay. Now, since delta t is very small, if you take the powers as squares and cubes, it becomes even more negligible, for which I have written an example here. That is, if it is 0.01, then squaring and cubing makes it even more negligible. Hence, neglecting higher order terms of delta t, the probability that there is no arrival in time lambda t would be delta t, small delta t would be given by minus 1 minus lambda t. Okay. Probability that there is one arrival in time delta t would be given by lambda delta t. Okay. Probability that there is one arrival is lambda delta t. Probability that there is no arrival in delta t would be 1 minus lambda delta t. Yeah. Next important parameter of a queuing model or of a queuing system would be the service time. How much time a person is, at the counter, how much time it is needed for a person to get service done is the service time. Okay. Now, lambda is a mean arrival rate. Mean service time is denoted by mu. It can be constant. It means what? For every 5 minutes, the service can be finished off. Okay, suppose if it is not done by humans and if it is done by a system, easily there will be a constant way of doing the service. Okay, so can be constant or it can be a random variable as well, guys. Okay, the service time also follows negative exponential distribution is the assumption. Okay, of course, the Erlangian distribution. Now, let g of t denote the probability that the service time is t minutes, guys. Okay. Probability that the service time is t minutes. Mu e power minus mu t is the probability distribution function. Okay. G of t is given by mu e power minus mu t. Why? For simple reason. It is following negative exponential distribution. And the averaging parameter, I mean the mean service rate is denoted by mu, guys. Okay. Yeah. Coming to the probabilities. Same thing like how I have done previously. Probability that no unit is getting served. No unit served in time delta t is given by 1 minus mu del 1 minus mu delta t. Okay. Probability that 1 unit is served in time delta t is given by mu delta t. Okay. This is how service time is calculated. Of course, in the video in which I have done the Poisson birth and death process, you can see all these things being taken care of. Okay. Yeah, this is just the basic parameters for the queuing system. So I'm talking only about the basics and not going into the Poisson birth and death process. Okay. Yeah. Now coming to the fourth parameter, that is capacity of the queue. Fourth parameter is capacity of a queue. Okay, capacity of a queue. Usually, there are anyways two types, infinite capacity or finite capacity. Okay, we have both the cases, guys. We have both the cases. So, let me explain. Infinite capacity, if the number of persons allowed into the queue is more than 20, if the number of persons You remember this 20, right? Number of persons allowed into the queue. Into the queue is more than 20. Yes, more than 20, then queue is said to be infinite. Queue is infinite. Okay. Yeah. Now, we can see Y20 as I was telling you, remember? Y20, I was telling you, remember? If n greater than 20, it's a large sample. If n less than 20, it's a small sample. We have discussed the same thing in testing of hypothesis as well, guys. Okay. So, example is, I can say here, more than 20, na? So, Q in cinema theaters, I can say. Okay, Q in cinema theaters can be considered as an infinite Q. Now coming to finite Q, guys. Capacity is finite. Finite capacity means obviously when I have put a bound as 20, less than 20 would be an finite Q. If the number of persons allowed in the queue are less than 20, then Q is finite. Okay. So usually we find queues to be very, usually we come across finite queues only. One example can be the queue at the barber shop. Even service, when cars are getting served, water wash or some service, there is a finite capacity only. Unlimited cars, unlimited trucks or unlimited trains cannot be served or cleaned at a time. So those such queues are all of finite capacity only. Okay. Yeah, there is also one more parameter, that is the capacity of source. Capacity of source you is an optional one. We usually don't take into account the capacity of the source. It can be neglected here. Of course, from the source from which people are coming can be infinite, can be finite, but then that can be skipped off here. Okay, that's not of much importance to be taken care of. Okay, yeah. The next thing, the fifth parameter that has to be taken care of is the number of servers, guys. Obviously, there cannot be infinite servers. Okay, so number of servers can be classified as a single server and multiple server. We don't have, by the way, we have only single server queuing models. Multiple server queuing models we don't have. So we can just skip off with small awareness towards what exactly it is. Okay. Yeah. If single server means just one person to serve, one person or one system, or one counter also I can say. One counter. The ones we come across in bank. Okay. So if the number of servers in the system are is equal to one, then it is a single server model. More than one, it will be called multiple server. More than, it will be called a multiple server model. Okay. Yeah. So after this parameter, the number of servers, the next interesting parameter or important parameter would be the queue discipline, guys. Queue discipline. Queue discipline means what? How the queue is being served or considered. Okay. There is this first come, first serve. Whoever stands first in the queue? FCFS or first in, first out, FIFO or FCFS. Okay, what that is this? Whoever comes first will be served first. That's one queue discipline. First come, first serve. Okay. Also this LIFO, Last in, first out, or last come, first out? Last in, first out. Okay, LIFO. And then there is also CIRO. Okay, there is also CIRO. Service in random order is CIRO. There's also priorities, guys. See, immaterial of the length of the queue, etc. The senior citizens, the politicians, kind of people are given priority. So there is also this discipline called priorities. Of course, again, it's optional. If it is omitted also, it's fine. Three disciplines, basically, you need to discuss the Q disciplines, FIFO, LIFO, and CIRO. If you are asked to describe or discuss about a queuing model, you will be discussing three Q disciplines majorly. Okay. Yeah. After this, after the Q discipline, there is also an important factor called the customer behavior. There's also called the seventh point is customer behavior. Yeah, I discussed about this in the class as well, guys. Customer behavior. First thing is bulking. Second one is reneging. Third one is jockeying. Again here, yeah, I think this one I'll omit here. Instead, I'll include here. Okay, bulking is nothing but looking at the size of the queue, the customer is hesitant and he doesn't enter the queue. A customer does not enter the queue, does not enter the queue when queue length is long. Queue length is long. Okay. He has no patience to wait. Okay, that's called bulking. Reneging is nothing but customer leaves the queue due to impatience. Customer leaves the queue due to impatience. See, he has some work or he got irritated with the situations around, so he left the queue. That's what is called reneging. Jockeying is simple, guys. He shifts from one queue to the other, thinking that the other queue is less or it is getting clearer at a faster pace. He keeps jockeying from one queue to the other or moving from one queue to the other is nothing but jockeying. Customers move one queue to other. When one queue is when there is more than one queue, there is more than one queue. When there is more than one queue, he keeps moving from one queue to the other. If there is only one queue, there is no other option. Okay. Yeah, some customers are served before, regardless of the order in which they arrive. Okay, as I have discussed about that, that's nothing but priorities. Again, as I have said, it can be omitted. Okay. Yeah. The final, I mean, the out of all the major ones, the final one would be the state of the system. State of the system. Simple. Whether you're talking about the system with respect to time or without time, if you're talking about, it would be called steady state. With respect to time, if you're talking about, it is called transient state. Transient state. In transient state, differential equations come into picture in queuing system. Okay. For a steady state, the differential derivatives go to zero because it's constant. Derivative of a constant is zero. Transient state, a system, when its operating characteristics are dependent on time, it would be called a transient state. Okay. Yeah. Steady state, independent of time. Okay. Yeah. Yeah. These are all the 8 elements or parameters of a queuing model. If you are asked to describe a queuing model, these are the things that you will talk about. First is the input or the arrival pattern. You cannot omit the inter-arrival time because the time between each two arrivals also has to be taken care of. Next, the service time. Of course, inter-service time also can be calculated. All this follow service time and arrival time, inter-arrival time follow negative exponential distribution. Arrival time follows Poisson distribution. Next thing, the fourth point would be the capacity of the queue, finite or infinite capacity. Fifth point would be the number of servers, single or multiple server. Sixth point would be the queue discipline, first in, first out, last in, first out, service and random order. Okay. Next is the customer behavior, bulking, reneging, and jockeying. The last important point would be the state of the system being in transient or steady state. Okay. These are the basic points that have to be taken care of when you are discussing about a queuing model. And then the Kendall's notation also take care of all these things. In Kendall's shorthand notation, we take care of all these things and notate them. Along with this, yeah, you are aware already of rho, that is the traffic intensity. It is nothing but the ratio of lambda by mu. Of course, guys, if the servers are more in number, then it is S into mu, guys. If S is equal to 1, this is the formula. 1 into anything is itself, right? So, if server is 1, then it's lambda by mu. If servers are more, lambda by S into mu. Okay? Yeah. This can also be written as rho is equal to 1 by mu by 1 by lambda. That's nothing but mean service time by mean arrival time. Mean arrival. Okay, again it gives the same thing. As I have told you, Erlangian comes into picture because unit of traffic intensity is assumed to be Erlang. Okay, yeah. There are some 1 or 2 important points regarding this traffic intensity. What that is the necessary condition. There is one small note. What that is the necessary condition for a system to settle down to a steady state. The necessary condition for a system to settle down to steady state is the traffic intensity should be less than 1. That's nothing but lambda by mu is less than 1, which is nothing but lambda is less than mu. Okay, or in other words, arrival rate should be less than service rate. Okay, yeah. Suppose if the arrival rate is greater than the service rate, the number of units in the queue tend to increase indefinitely as time passes on, and hence the queue becomes uncontrollable. Okay. Yeah. On the contrary, let this be A. On the contrary, if rho is greater than 1, that is arrival rate is greater than service rate, the number of units in the queue tend to increase indefinitely as time passes. Okay. So, traffic intensity is also the parameter, the important parameter with which we derive remaining things in the queue. Okay. This also has to be taken care of when we are talking about queue discipline. I mean, things related to queue. Okay. Yeah. I'll just stop here.